Hello everyone, this is Wuyang Li from the Chinese University of Hong Kong. Today I'm excited to be here to talk about our work entitled CLIF, Continual Latent Diffusion for Open Vocabulary Object Detection. In this work, we aim to address the challenge of open vocabulary object detection. Different from traditional object detection that can only detect the objects from predefined categories, as shown by the red bounding boxes. Open vocabulary object detection aims to identify any novel class objects using a class name vocabulary provided by the user, such as the elk, this figure. To achieve this objective, we begin with a baseline model that leverages the Vision Language Foundational Model, CLIP, to enable novel class detection. First, the image is sent to the object detector to generate object embeddings. Next, they perform a distillation using the image embeddings produced by the CLIP image encoder, and use the CLIP text embeddings to optimize class separation. Then we will discuss the limitations of this commonly used pipeline. Firstly, this paradigm directly optimizes class separation using predefined base classes in a discriminative manner, overlooking the underlying distribution and alignment. This can lead to bias towards base classes and reduce the generalization ability to open set scenarios. The second challenge lies in the inherent conflicts between the two optimization objectives. We first conducted a statistical analysis of the cosine similarity between the CLIP image embedding and the associated text embedding of region proposals. Our findings reveal a significant angle between the two embeddings, suggesting that directly using these combinatorial objectives results in suboptimal performance. To address these challenges, our research question is how to model an explicit distribution transition among the object, CLIP image, and CLIP text subspaces without combinatorial conflicts, enabling distribution alignment and harmonious optimization objectives. To answer this question, we first revisit the state-of-the-art probabilistic model, the diffusion model, treating this process as a gradual transition from the Gaussian distribution to the data distribution with dense hidden states. Driven by this formulation, we propose a continual latent diffusion pipeline for open vocabulary object detection. The key idea of our method is to model the transition from the object embedding space to the CLIP image and text spaces. Notably, we choose the CLIP image as the middle space because it shares visual representation with the object space and is coupled with the CLIP text embedding through CLIP pre-training. Now we well introduce the technical details of our method. We first send the input image to a common object detector to generate the region proposals and object embedding. Then we lift the object representation to a probabilistic space using variational encoding, which models the hidden object space with a multivariate Gaussian prior. We deploy two separate fully connected layers to estimate the mean and variance vectors and introduce the KL divergence to enforce the Gaussian constraint. In this probabilistic object space, we further conduct sampling using the reparameterization trick, and we name sampled vectors as object-centric noises because they not only contains instance-level semantics but also satisfy with the normal Gaussian. For the generation process, we use the sampled object-centric noise as the initial state of the diffusion process and generate CLIP image embeddings through a short-distance object-to-image diffusion. Finally, we perform a long-range diffusion to generate text embeddings with the guidance of the generated image embedding, achieving a well-alignment between the object and text distribution. Here is a visualization and comparison of the new class objects. We can see that existing works wrongly recognize two overlapping cats as a couch due to the visual similarity, but our method can identify each cat and give the correct prediction. Next, we compare our method with state-of-the-art approaches on the COCO benchmark. Different from existing methods that transfer object space to text and image separately, our approach enables continuous transfer among all three subspaces. This innovative design leads to significant performance improvements over the baseline model. Finally, I will give a summary of our work. First, the proposed CLIF framework lifts the object embedding to the probabilistic space via variational auto-encoding, achieving an explicit modeling of object distribution. Second, CLIF achieves a continual distribution transition among multimodal subspaces, transferring the object the CLIP image and text subspace. As a byproduct, CLIF makes a connection between variational autoencoder and diffusion model. Thank you for your listening.